We have a short business meeting just to go over some announcements first, and then we'll have our guest speaker. Turn that down. Maybe that's not me. No. No, it is picking up a little bit, I think.
Actually, your heart.
There we are. I've got a big heart. I want yours a small heart. Anyways, so I'm Chris Burst. I'm the Senate President, and I'd like to welcome everybody here. Are there any visitors tonight? Welcome, welcome. We have some complimentary copies of the Sky News magazine, if you'd like to pick one up before you leave. This comes out 6 times a year, and it is part of one of the benefits of being a member. You get a subscription to that. So on tonight's agenda, for the announcement portion, I don't think we have any observing reports unless somebody has found some clear skies to look through. I think we've done a little bit, but not much. We'll have our announcements, some upcoming events, and we're getting into our outreach season, so we have quite a few upcoming events to talk about. We'll have our guest speaker, and then after the meeting, there is coffee, tea, and cookies in the Elliott Building 4th floor lounge. So that's in the office part of this building on the top floor. So go that way, I guess it is, and yeah, into the other part of the building and up the elevator or up the stairs. Okay. So some of the announcements, membership, we have 272 members as of today, but 13 of those people have memberships have expired in the past 2 months. So if they don't renew, we'll be down a little bit. I don't think I have too much else to announce. Just to say that somebody has been trying to scam us again to get money out of the center. So I did mention that in my monthly report, just as a reminder to everybody to be vigilant when when you're getting emails and people ask you for money. I was supposedly asking people to personally pay for something for the center. So that was quite interesting that somebody would try and pick on us, but worth being vigilant. So I think that's all I have. Reg, do you have anything from your portfolios?
Hello, everyone. From the Sky News editorship, they cover this month a beautiful picture of the moon, Jupiter, and Mercury. The moon, Venus, and Mercury, taken by new club member Randy Inkin. And it inspired an article about Venus, so it's called Venus, Our Neglected Neighbor, Read It and Weep. So I have extra copies, a limited number of hard copies if people would like them. Please approach me at the end of the evening.
Great, thanks, Reg. Debka is not well tonight, so she's not here, and Joe is on the traveling. So Bruce, Treasurer's report.
Chris Lane, your treasurer. Our current members accounts down to 7,320. All our paperwork is in. The process of getting my personal PCEID transferred over so that they can get a society one. I've spent many hours trying to do that because they don't know how to do that. Services BC isn't exactly what you call best of breed. So they don't all the people who know what they're doing are elsewhere. But not much. Hopefully they'll be fixed things here. And other than that, that's pretty much where we're at. We've gone, Deborah Crawford and I are basically at the hunt for our next Star Party venue. We have been to many, many places, been turned down by even more places. We're basically looking at, I'm still in contact or something like it with St. Stephen's Church. Deborah's also in contact with some other group. I'm waiting to hear back from yet another group. So we are contacting people on a regular basis and going to most of the people. If you yourself have a very large property that loves getting extra parking and has a nice dark sky site, let us know. That's all.
Thanks, Bruce. And just while we're talking about money and fundraising, we have a limited supply of the plastic Big Dipper glasses that go with the beer that has been made in honor of the centenary of the plastic telescope this year. So if you are interested, we are selling the glasses for $8 each, or two for $15. So I do have some here, and Bruce can help take the money, I guess. Right there.
Well done.
Yeah.
Good picture.
Yeah. So yeah.
That's not.
No, well, I don't want it to roll off. So that's what it looks like as a glass. I don't know if you can see that. So I'm just using the document camera. Anyways. Okay, so we're now down to Outreach Coordinator Ken. Some big events coming up.
Big events, yes. I've been handing out posters for Astronomy Day. Well, they're not really a poster, but if you can put them up at a grocery store or someplace where people will see them, I'd appreciate it. It's for all the pub. April 21st, if you want to be involved in Astronomy Day and I haven't approached you already, please see me. After that, when is May 23rd? Is when we need to have the table in the conference center? Wednesday, I think it's May 23rd.
Yes, I think you're right.
We need some volunteers to attend the conference center that Bob McDonald is going to be attending. May 23rd down at the conference center down on Douglas. So if you want to attend the table for a night, we'll be able to see the speech as long as we attend the table afterwards. After that, we have the Strawberry Festival, the early part of June. We want solar viewing for anybody who shows up for the Strawberry Festival. And then we have Fort Rod Hill, which is August 10th. So those are the main events that are coming up soon. Thank you.
And just a reminder that starting on Astronomy Day will be the first of the nights at on the Hill. And they are going to continue every Saturday from the 21st of April until the 1st of September this year. No breaks. So some of those days will be rather late darkness or virtually no darkness. So, you know, we'll do what we can. And there are some plans through the Friends of the Dominion Astrophysical Observatory to have 2 special nights during the summer. One to commemorate the actual first use of the telescope, which was at the beginning of May 1918, so it's the 100th anniversary. And they want to have a fundraising night on one of those as well. So one will have tickets for sale. But we will need telescope, sidewalk telescope people. So if you've done that in the past or not, and you'd like to contribute to that, please let me know. We'll be needing some people throughout the summer, and there will be 20 opportunities to participate in that. Schools program, Sid.
Lucky for us, school program is almost winding down. However, we have 10 more presentations to make. And this includes a couple of night sky viewing sessions, different locations. I will be in touch with you with prospect volunteers for night sky viewing. And it's almost over. The season is almost over.
Great, thanks. So you've done a lot of visits this year?
Yeah.
Still more?
We did 66 so far and 10 more to go.
Great, thank you. So one of the things that Ken mentioned was that the professional group of astronomers are having their conference here the week of Victoria Day long weekend, so it starts right after that. And that is where there will be an open talk that Bob McDonald's giving, and we would like to have an information table there as that's open to members of the public. But Jim, I don't know if you have anything else for our attention?
Well, I had hoped to get an email out before tonight, but things are crazy with EAO 100 preparation. The response from RASC members to ask to attend the conference and registered for the very low fee has been very high. And something we didn't anticipate is that a lot of people from the RASC have signed up to attend the lunch talks, which include an exceptionally expensive catered brown bag lunch. That's not included in the price that the RASC people have paid, and we regret that we did not make that clear. So I'll be letting everybody who signed up and registered for the lunches know that they will not be receiving one of these ridiculously expensive brown bag lunches. Unfortunately, so you'll have to bring your own lunch or go to one of the many eateries in the conference. Otherwise, the turnout has been excellent. There are 275 people are in total are registered for the meeting, the talks. The number of truly excellent contributed science talks is overwhelming. Now we're going to cull them down to the 45 slots we have. It's going to be a wonderful meeting to celebrate the centenary of the plastic telescope.
And the registration is still open, is that right?
It's now in the, beyond the early registration, the fees have gone up. It's open until the conference begins.
But just to remind people that if you are a member of the Royal Astronomical Society, you can take advantage of a lower rate to attend some parts of the conference. But as Jim said, if you do pick a lunchtime one, you don't get a lunch. National Representative Nelson.
Yes, we had a national council meeting on Sunday last, and it was a couple hours long, and the most of the people attend via WebEx. And the two principal things that were discussed were the first, and I don't know much about this because not much was said about it, but the RASC national organization has subscribed to a remote telescope. And I think further details are forthcoming.
They bought it. They read the pier in the spot, but they bought the telescope.
There you go. So they rent a pier, don't know where it is, and they bought a telescope for it.
Hopefully it's somewhere clearer than here.
Yes, it's a nice site in California.
Yeah.
And we got quite a deal on the telescope too.
Anything updates on the bylaws, which is kind of the other thing you're working on, and revision thereof?
The bylaws, we had at our last council meeting, the bylaws have been posted, and we have solicited comments, and I've gotten one set of comments from Sid, and in a general way, I'm going to incorporate those into a new edition and circulate.
Just as background, we have to, under the revisions to some of the laws, update our constitution and bylaws to conform with a new standard. So we will be working on that. Hopefully we can put it to membership as early as next month, because that was our hope, I think.
Yes.
For the review period.
Yeah.
So look out for that information coming up about that. Technical committee, Matt, any updates?
Yeah, we had a very busy Saturday, 2 weekends ago now. Took off the scope, remounted the scope, installed a safety backup on the scope and the mount so that the scope will never slip off the cradle. Additionally, some new cabling and so on, and we have successfully guided with the guide camera, which is the first for that. Dan put out a report about that. More to do. Focusor is the next battle, and it's just about ready to go.
Great, thank you. Any questions about that? Great, and Michelle's not here this evening, so, and as I said, I don't think there's been too much observing. Here are some of the events. The Victoria Centre Observatory is currently on Saturdays and will be switching to Fridays soon, once the Saturday star parties open. You do have to be on the active observers list to be included in that. Astro Cafe will be continuing through May. That's on Monday evenings. We are scheduled to have the UVic Observatory this Friday. The weather forecast is looking pretty dismal at the moment, which I think we've only managed one so far this year. I will send out a go, no go announcement depending on what happens. Just a reminder that Astronomy Day is coming up. It's on Saturday the 21st, and that will be the start of the season of summer star parties as well, which have been mentioned. Does anybody else have anything else that, Nelson?
I did forget one thing. The principal thing that was discussed at the meeting was the annual General Assembly. And Chris Gaynor is sort of heading up an investigation of the best way to conduct the General Assembly. And I'm talking about having them every other year, having smaller ones, having larger ones, all that kind of thing. So if anyone here has any suggestions or thoughts about the conduct of the annual General Assembly,
I'm the guy.
Yeah.
let him know.
And this year's assemblies in Calgary
This
are
year,
around Canada Day, right?
yes, the 28th to the 1st. We already know next year it's going to be in Toronto around the 20th of June. And it's going to be a joint meeting with the American Association of Variable Star Observers. So
Be interesting.
that'd be fun.
One of the issues that the society is realizing is that the cost of things going up. You know, Jim is mentioning these expensive bag lunches. Well, even renting a venue such as the one you're sitting in at the moment, the costs are continuing to go up. So it gets very expensive to hold one of these conferences, and people have to try to spend money to get there. So the attendance isn't always what I guess we'd hope it would be either. So if you do have ideas, yeah, maybe it is time or to divide it up more regionally. Virtual connections, things like that. Jim.
One more event that people, it's happening on the 4th of May. How much of an event is actually going to be, we don't yet know, but the exhibit on the DAO Centennial is opening at the Royal British Columbia Museum. It's scheduled to open on the 4th of May. Whether they're going to make an event out of it or it's just going to appear is TBD. But if the exhibit will open on, is scheduled to open on the 4th of May, it will be at the museum until the July 1st weekend when it moves up to the center of the universe for the rest. And it is, they're professionals. They are doing it very nice.
Yeah, thanks for the reminder about that. Are there anything else to remind us about or tell us about, or did I forget? Hearing nothing further, I guess it's time for Reg to introduce our speaker.
Everybody's over on this side of the room, so. At any rate, our speaker tonight is Henry Nong, Dr. Henry Nong. And some of you might have actually met him before because he did give us an interesting talk at the Machosin Star Party last summer. And at that time, Henry also brought his wife along, and his wife was expecting. And in October, they gave birth to a baby boy who's now 7 months old. So besides starting a new job here, he's a new parent, and I'm sure the last 7 months have been a big blur for him. We can see a before and after thing. People can see how his presentation goes tonight. But he was born in Mississauga. He grew up in Richmond. He got a bachelor's degree at UBC. And then he went and got a master's degree at Queen's University in Kingston. And then he spent 5 years at Caltech getting his PhD in planetary science. And this gave him an opportunity to get his hands on some of the big scopes like Palomar and the Subaru telescope on Mauna Kea. And he's going to share a bit of experience about working on these big scopes. And we'll keep that in mind when we're operating our VCO 16-inch. See how that is. But his talk tonight is called Hot Jupiters, Super Earths, and Mini Neptunes. Oh my. So it's going to be an interesting talk, and I thank Henry for preparing this and taking the time to come and talk to us tonight. So
thank you, everyone, for welcoming me to your meeting. Thank you again, Chris and Ray, for inviting me back. I guess I didn't do so bad last time in July. So, how many people saw my talk in July and were chosen? Okay, so a handful. So there'll be a couple of things that are the same again, but I actually tried to make this a little bit different, and especially near the end, I'm really going to share my story of how, well, the story of like going to Mauna Kea to observe, and also going to Palomar to observe. So the last part will be just mostly pictures and just talking about observing adventure, and I hope you enjoy that. For today's talk, feel free to just raise your hand and ask questions whenever you want. This morning, I was actually with a third grade classroom talking to the third grade class about exoplanets. They have tons of questions. So I'm all rolled up for questions, and I'm excited to compare your questions with their questions. No, just kidding. No pressure. Yeah, so as Red said, my name is Henry Rowe, and I recently grew up in BC, spent some time away to do school, but I'm really happy to be back in BC again. And I'll be telling you about my research that I've been doing during my PhD, but also right now as a postdoc at NMC Pittsburgh. So the work I'm working on, the stuff I'm studying are exoplanets. Right? These are planets that are found in other star systems. And up here is a picture, an artistic rendition of one of these exoplanets. The star is in the top right corner, and this is just a really hot planet. It's really close to the star. It's very rocky, maybe because it's so close to the star, all the atmosphere has been stripped off by the solar radiation. But before we talk too much further about exoplanets, excuse me, we really should be talking about the planets in our own solar system. Right? We need some kind of baseline comparison to compare these new planets that we've been finding with something we are able to study a bit easier. We can send robots to, we can take pictures of, we can look at in the night sky and observe them with our own telescopes directly. So here's a portrait of the 8 classical planets in our solar system. Right? We have the 4 rocky planets that are close in, Mercury, Venus, Earth, and Mars. Then in the middle, we have the biggest planet, the gas giant planets. There's 2 of them, Jupiter and Saturn. And then in the distant edges of the solar system, we have the 2 ice giants. And just to give a sense of how far away these things are, because these pictures, the size of the planets are to scale, but the distances between them are definitely not to scale, right? So from the sun to the Earth, it's 1 astronomical unit. That's the kind of unit we like to measure things in the solar system. Jupiter is up to 5 astronomical units, and Neptune is up to 30 astronomical units. I apologize if some of this is very familiar to you already, but I just want to make sure we're all on the same page. And we look at the architecture of the solar system, it is a little interesting, right? Because there's no clear pattern to how the planets are structured. For example, you might expect the planets to go from smallest to biggest, either going upwards or inwards, but we don't see that. We see the smallest stuff on the inside, we see the biggest stuff in the middle, and then way out here, instead of getting the really small stuff, we actually get quite big, weirdly big things as well. So when we look at the solar system, we have to come up with a planet formation theory that can explain all 3 types of planets in our own solar system. And so I'll tell you a story of how we think planets formed before the discovery of exoplanets, when we only had these 8 planets as our data points. So here is one story. So this is a protoplanetary nebula, where basically the sun 4.5 billion years ago, before the planets really started forming, And there's still lots of gas everywhere. It's a very messy place. There's lots of gas, there's lots of dust, it's very dirty, there's lots of rocks around. And these rocks start combining with each other. So they start colliding, and two rocks at a time. And when two rocks collide, sometimes they can grow into a bigger rock. And then it can collide with another rock and grow into a bigger rock. And you can grow and grow and grow until you get to something the size of the Earth, or even a little bit bigger than the Earth, and that's how you can start forming some of this plant. So if you zoom in here, there's how you can see how some of the plants grow. And then, so that takes care of the rocky solid stuff of the planet. So that's the 4 rocky planets, and the cores maybe of the giant planets. But how does the big atmosphere get onto the planet? So here's one story, one scientific theory. Right? So first you form the cores, like I just said, by combining small rocks together. Then the next step is, if this happens fast enough, the gas is still around, so you can start accreting on the gas. So you start growing and growing, you just slowly suck in some gas, and you start growing an envelope, which becomes your atmosphere. And then at some point, you reach an instability. And this instability happens when the amount of mass in your atmosphere is about the same as the solid core. And this is a huge amount of atmosphere. It takes a long time to get to this stage, but because for comparison, on the Earth, our planet is mostly solid. It's a very thin atmosphere. But on these protoplanets, the atmospheres are super thick. And you get to this runaway equation, and then whoop, all the gas kind of just collapses onto the planets in a matter of less than 1 million years. Tens of thousands of years, which is very fast in the astronomical timeline. And then eventually, everything goes away, the gas dissipates, and then the planet starts contracting. And so the giant planets, we think, began at really large, big balls of gas, and then they slowly contracted. And as they contract, they release heat, they release energy, because all this energy was used to put the gas together. It has to go somewhere. It starts radiating out energy, and then we can see them with a telescope, because this energy and heat is light, right? We can actually try to observe it. So this story kind of works pretty well for our own solar system, because when we think about how the planets look up here, it kind of explains why the rocky planets, which form in the inner part of this, there's less stuff up here. So that's why you form the smaller planet, or so the story goes, right? Then in the middle, you can form a gas giant planet. You form the solid cores, and there's still plenty of gas up here. And it doesn't take too long for one object to orbit around here, so that you still can suck in a lot of gas and grow into the big gas giants. And then the reason why we have the smaller ice giants out here is that way out here, it takes a lot longer for a rock to go in an orbit around the sun. Right? So something like Neptune at 30 AU will take almost 200 years to make a whole circle, a whole orbit, right? So if it takes about that long to completely orbit, that's about how long it takes for 2 rocks to encounter each other, which is much longer than something like Jupiter at 5 AU, which only takes about 10 years. So because it takes so long to form for rocks to collide with each other, it takes a long time to form the core, and by the time the core is ready to suck on all the gas, most of the gas is already gone. And maybe there's less gas up here because you're further away from the star. So by the time these giant planets are ready to go unstable and form all these gases, there's less stuff around, they don't form as big. And then that can explain the ice giants. Yeah, question.
Given that timeline, are there planets still forming?
In our solar system?
Yeah.
So we don't think there's planets still forming in our solar system, because what happens here, so in this picture, it's still a very dirty, messy place. Lots of gas, lots of solids, but quickly after these last planets form, the gas completely goes away. It only takes tens of millions of years at most. And then what happens to all the dust? They're kind of all, they fall into the sun. There's some drag forces that suck them into the sun. But at the same time, you might heard about solar wind, right? And solar radiation, and that kind of flows up from the sun, pushes the dust away too. So now we have a pretty clean solar system. You look, I mean, this is just a cartoon, right? But if you look at how the solar system looks right now, there's actually not too much stuff between the planets. There's the asteroid belt and the Kuiper belt beyond Neptune. But other than those 2 main asteroid belts or rocky areas, our solar system is pretty clean. There's not too much stuff going on. So there's not things that can still form planets. But that's a good question. So I told you this story about this nice thing where we only have 8 data points, only 8 planets we had to worry about. And of course, maybe the story is still correct, but now we have to think about a new way of forming planets. So in 1992, one of the first exoplanets discovered was discovered on a pulsar. So this is a pulsar here, and here's some artistic rendition of some planets. And the pulsar has a weird name, but that's the name of the planets now. PSR B1257 plus 12. Okay, so actually this is, I think, related to the coordinates of this object, but it is a pulsar, and there's actually 3 planets around it. There's a 4 times the Earth mass at half an AU, 2% of the Earth mass at 0.2 AU, and another giant planet 4 times the Earth mass at 0.36 AU. And this kind of changes the story of how planets form. Because if you remember, in our solar system, Mercury is 5% of the Earth mass at 0.4 AU. And this guy is 4 times the Earth mass at 0.5 AU. This guy is also 4 times the Earth mass at 0.4 AU. So in my first story, I said the inner stuff, when you're looking really closely, you can't form big planets. You only form things that are 5% of the Earth mass. But with this one of the very first systems we discovered, we have stuff that's 4 times the Earth mass at the same distance. So what's going on there? And another thing to think about is that a pulsar is actually a very evolved star. It's a star that's gone through the whole, so our sun is a main sequence star, right? It's burning hydrogen, creating a lot of light, but eventually all the hydrogen runs out, and then the star dies, and if the star is big enough, it becomes a pulsar. In order for the star to do that, it kind of goes through a giant phase, and the star grows to be really, really big, and engulfs all of its inner planets. So these planets are only half an AU away, would not have been around before the star became a red giant and became a pulsar. So these are so-called second generation planets, we think, that formed after the star became a pulsar. So right now in our own solar system, there's no planets forming right now, but in 5 billion years when the sun dies and becomes a red giant and then becomes a white dwarf, the remaining material left over from that, not explosion, but the destruction of planets, because the sun will probably engulf everything up to Mars. All the leftover material could form second generation planets, new planets. So these planets form very differently from the story I had just told you about our solar system. So yeah. The other interesting thing to think about is that these planets are 4 times the Earth mass. They're kind of bigger than the Earth and smaller than Neptune, which is about 17 times the Earth mass. And in our solar system, there's actually nothing in between the mass of the Earth and Neptune, or Uranus and Neptune, ice giants. So this type of planet, something that's 4 or 5 times the Earth mass, is not in the solar system, but very, very common around other stars. So we have to give these objects a name, and we call them super-Earths because they're slightly bigger than the Earth. So that's the name that astronomers have come up with to kind of classify this very common type of planet. Yeah, so it's a very pretty picture. And it's one of the first exoplanet systems that we discovered. It kind of really made us question, do we really understand planet formation from just the 8 planets in our solar system? And then, so you think this kind of threw everything up in this way. There's another discovery in 1995 that really confused everybody. And this one is called 51 Pegasi b. And it's a hot Jupiter. Right? It's a hot Jupiter because it's almost the size of the mass of a Jupiter. It's half a Jupiter mass, which is 150 times the Earth mass. And it's only at 0.05 AU. So this is even closer than those super-Earths we found. It's 10 times closer than the orbit of Mercury. It only takes 4 days to orbit the sun. And this is a giant, gas giant planet. It's half a Jupiter mass. So how did the planet form so close to the star? And this kind of also really made us rethink our planet formation model, because nothing in our current models can explain this. Did they form? Right now, the 2 possibilities we think about are maybe there is a way to form such giant planets so close to the star that we just didn't know about yet. Or they really formed kind of like our Jupiter and then somehow migrated inwards a little bit. So I told you about the 2 of the first exoplanets discovered. And actually, a common question is, what is the first exoplanet discovered? And that's kind of a tricky question because and this postcard or this picture, this poster from NASA kind of tries to get around that question. So there's 51 Pegasus IB we just saw. There's a hot Jupiter, and some people call that the first exoplanet because it's the first time an exoplanet was confirmed to be discovered around a star that was like our sun. Right? It was a sun-like star. There's PSR B12 something. Right? That's the pulsar planet I just talked to you about before. Some people say that's the first confirmed discovery, and then but it's not really around the same kind of star as us. It's around a pulsar. It's a little different from a sun-like star. And then there's two other objects. There's HD 114761b, and that was discovered by Dave Latham in 1989, so before these other two planets. And Dave Latham, who's an astronomer at the Harvard Observatory, Harvard University. But that object at that time, the mass was pretty big. There was dispute whether it's actually a planet or just a really small brown dwarf. And then at the bottom here, there's Gamma Cephei AB, and that was actually discovered in 1988. And it actually has local roots. It was discovered by Bruce Campbell, who was also an astronomer at that time at the DAO, where we work, and with collaborators Gordon Walker and Stevenson Yang, who are now emeritus professors at UVic. But Gordon Walker and Stevenson, I think, were at UBC at the time of the discovery. So there was a giant planet around 2 AU, so not quite a hot Jupiter, but chronologically it was the very first discovery. However, at that time, no one expected to see giant planets at that close in separation. So, being careful scientists that they considered all the possibility and said it was more likely that it was something weird the star was doing that they were measuring, not a planet. So they did not claim it to be a planet. They published their detection. They said it's probably something weird with the star. And then about a decade later, other astronomers went back to the system, looked at it, and confirmed, yes, it was actually a planet. They did discover a planet. But then the official confirmation didn't become a planet in 2002. But then, so it depends really who you ask, which one of these four you want to count as the first exoplanet. But I like to count this one because of Victoria. So how did the first exoplanets were discovered? How did we discover the first exoplanets? The scientists use something called a Doppler effect, right? And you might know about this from experience and whatnot. But the Doppler effect for sound shows you that when you have something coming towards you, you hear a higher pitched sound when it's like coming towards you, and then a lower pitched sound as it goes past you. Right? This is a Doppler effect for sound, but there's a similar effect with light. Right? So you take the white light from the star and you put it through a spectrum. You know that the white light is actually made of many different colors, and then there's something called red shift and blue shift. If the way that the spectra that you look at moves a little bit towards the red and a little bit towards the blue, and it turns out that when something is moving towards you, everything looks a little bit bluer. When something is moving away from you, everything looks a little bit redder. But this is a very very subtle shift. You can't really use this to get out of a speeding ticket or running a red light. And you were going, it was moving towards you, so it was so blue, and you couldn't tell that it was a red light. You can't do that, but you can do this by you look at it carefully, measure the light from the star, and then you can kind of see a planet. So this is kind of what happens because of Newton's law. Right? If a planet is orbiting a star, the star actually moves orbits as well. The star doesn't stay completely stationary. There's a little bit of wobble with the star. And then here's a cartoon of what you can see, like blue light, and then as the star was going towards you, now it's going away from you, so the light looks a bit redder, and then it's kind of neutral when it's moving perpendicular to you, and towards you again, now it's a little bit bluer, then away, it's a little bit redder. So by looking at this wobble, by measuring the fact that the light from the star looks a little bit bluer, then a little bit redder, then a little bit bluer, then a little bit redder, you can infer that the star is making this kind of motion. And why is the star moving like this? Maybe there's a planet around it. And this is the radial velocity method of detecting exoplanets. And this is what this is the method used to detect some of the very first exoplanets. And it's still used today to measure a lot of exoplanets. Any questions about this method? Yes.
The gravity of the planet is causing the wobble of the star.
That's right. Yeah. So Newton's law is that every action there's an equal and opposite reaction. And so even right now, as I'm standing on the Earth's gravity is pulling me down towards the center of the Earth, but I'm actually also pulling the Earth up. But the mass ratio of me and the Earth is very, very different. you know, maybe after Christmas dinner, it's not so different, but my tug on the Earth is very, very small. And similarly, in this diagram, this motion of the star is exaggerated. The planet doesn't move the star this much, but it is just exaggerated so that we can see the effect. And that's why we need very, very sensitive equipment to be able to see the very slight wobble of the star. And that's why I took it to the last couple of decades to get this equipment to the level where we can detect this very small shifts. Yes?
So if somebody was way out and looking at our star, would our star have a wobble and a different radial velocity because of all of our planets?
That's right, yes, it would. And actually, they would, I think it will be Jupiter that will make the star wobble the most because it has the biggest mass. But yeah.
Do you know how much the wobble is?
That is a good question. It's a very common PhD exam question, but I studied for this exam and then, you know, like, I don't remember the exact number anymore, but it is on the order of maybe 10 kilometers per second. So, yeah. I mean, 10 meters per second, sorry, yes. 10 meters per second. And I guess, I don't know if that even makes sense because it's a radial velocity. So if it's a wobble equivalent to something moving 10 meters per second away and towards you. But I don't know the exact number, but it's about, yeah. Any other questions? Right, so, oh, yeah?
So a star with no exoplanets would functionally have zero wobble.
Well, so that is a little tricky. So there's lots of other things that move. So stars are moving in space as well. So since stars orbit the center of the galaxy that they live in, so there's some motion. It wouldn't be a wobble, but there'll be some radial velocity. So when you measure it, it will never be a zero velocity. The way we actually measure planets is that you measure an offset to the velocity based on some other linear or some other trend and some baseline. So you measure the star's radial velocity, you see some baseline, and then you see some departures from the baseline. Sometimes it's getting a little bit higher than expected, sometimes a little bit lower than expected, and that's what the planets is causing it.
So there's a wobble threshold where you assume there's an exoplanet.
Yes, or to flip it around, it's more like there's a sensitivity threshold where we know for sure there's something pushing the star around, and it could be an exoplanet, or it could be another star. It could be two stars. If it's far enough away, or the angle is a little bit different, we'll see the wobble a little bit different. Yeah. So you may imagine that this is not a very efficient way of detecting exoplanets. It's a very good way of getting information like the mass, because the bigger the planet is, the more massive the planet is, the more the wobble rate. So we can measure masses of the planet in that way. But it does take a lot of time to these type of measurements are very they require a lot of time to do, and every telescope can only look at one planet at a time. So in the years after 1995, when this method was proven to be able to detect exoplanets, we got like maybe half a dozen to a dozen planets per year. You know, a good amount, very exciting still, but not a huge amount, because now we have thousands of exoplanets. So how do you get to a few per year to now thousands of exoplanets? And that's because there's other planet detection methods, and I'll talk about only one other one, and it's the transiting method. It's because and a lot of the planet haul that we have today comes from the Kepler Space Telescope. So this is the space telescope for a 1 meter diameter mirror in space. It was launched in 2009, and it's a NASA mission. This telescope is pretty simple in the sense that it is basically just a very giant camera, a 95 million pixel camera with very good guiding system so that it can stay very stationary, and it basically stares at the same patch of sky for the 3-year mission, the 3-year nominal mission that it had. And during that time, we looked at 150,000 stars at the same time and monitored its brightness. And the reason why it monitored its brightness is to detect planets, which with this method I'm going to show you. So again, we have a planet orbiting around a star, and now the perspective will shift to like a front view. And here you see how much light we're measuring from the star. And it's lots and lots of light. When the planet's in front of the star, it gets a little bit dimmer. So there's a big dip in this diagram. There's a big dip in the brightness. And then when the star moves away from the planet moves away from the star, the brightness goes up again. And so again, this is an exaggeration. It is a cartoon for explanation. in reality, the brightness is dipped down this much. But by monitoring the brightness of the star over time, we see periodic, repeated dips like this. We can infer that a planet is crossing in front of the star and causing this brightness difference. And not only that, we can measure the period of the planet by seeing how long it takes for another dip to happen. Right? That gives you the orbital period, which gives you a distance of how far away it's orbiting from the star. And we can also measure how much light is being blocked, because when you look at it here, when it's blocking the star, the shadow is basically proportional to the area of the planet divided by the area of the star, the cross-sectional area. So that gives you an estimate for, even though the star's radius, it gives you a good measurement of the planet's radius. So note that I said radius and orbital period, but we don't actually measure the mass this way. So a lot of times, stars that are planets that are detected with this method have greater velocity follow-up in order to determine the mass of the planet. And then when we have those two things, mass and radius, you can get density. Right? You can kind of figure out, is this a rocky planet? Is it a big poofy gas planet? Is it some kind of poofy cloud water planet, water world maybe? Any questions about this method? Yeah. So this bright and dark pattern is what informs us that there could be a planet possibly in front of it. And of course, there's lots of caveats. Right? You know that the sun has sunspots, so stars have star spots, and star spots when the star is rotating, the star spot can rotate into the field of view and out of the field of view, and that causes the brightness of the star to go bright and dark and bright and dark. So those things can mimic planets, and it's a little tricky to really have a difference between a fake false positive and an actual planet. Yes.
I have a quick question.
Yeah.
150,000 stars. So has all the data been analyzed already, or
yeah,
still more to be crunched?
So this, so all that data is back on the Earth now, and the scientists have them, and the NASA Kepler team have put them through the main pipeline and basically identify the most obvious, most sure planet. And one of the things that they do is that you wait for a planet to have 3 of these transits. Right? So can you see it once, you don't really know if it's a planet or not. It could be something else that just happens to make the star darker. But you see it 3 times all at the same time, and a bunch of other things they do to verify it as a planet. You know, you're more confident as a planet. So the official NASA team has produced a catalog of very certain to be planet, like 99.99 something percent certain as an actual planet. But there's still more work to be done, because those are only the most obvious and easy planets. And there's people, so I have some collaborators at UBC who are going to relaxing the constraints a little bit and are looking at planetary signals that where we only see the transit happen 2 times. And 2 times in a 3-year mission means that you're going a little bit further away. Right? These are always 1.5 years. It's kind of like Mars rather than the Earth. But so I'm working with them to use some other telescopes to kind of follow up and double check that these are actually planets, because when you're going down to only 2 transits of 3, you're increasing the risk of some false positive, and by doing other telescope imaging, you can kind of eliminate some of the false positive scenarios. So in some sense, yes, the main haul of planets has already been discovered, but there's still a little bit more to dig down.
Is the geometry such that you're going to under
That's right.
all the time?
Yeah, so I didn't mention it, but you look here, you only see the planet transit, and it just happens to line up right between you and the line of sight. And on average, it happens about 1% of the time. So for every planet we find, there's probably 99 other planets out there like it that we haven't seen yet. So now, oh, sorry, you have a question?
I was just going to ask, so this gives you an inventory of the number of planets in that 150,000 sample. And of the 150,000 stars, how many stars are likely to have planets?
Right, so based on all of our methods of detecting planets combined, we think on average, every star has at least 1 planet. So, Yeah, so like our solar system is not too unique. It might be unique that we have 8 planets, but and in the architecture I showed you at the beginning, but about every star system should have planets. So now, out of the known exoplanets, we have about over 3,500 known exoplanets, and here's a plot of how many we know over time. It's an exponential growth. It's growing fast. It's growing well. We're finding more planets every day. There's a big jump of them shortly after 2009 with the Kepler Space Telescope. But it's going to be another jump pretty soon. So I talked about the Kepler Space Telescope is actually winding down. Sometime in this year, it's going to run out of propellant and basically stop working completely. But on Monday, NASA is launching a new space telescope called TESS, the Translating Exoplanet Survey Satellite. And as you pointed out, Kepler only looked at one section of the sky for 3 years. So we know a lot about planets in that one section of the sky, but what about the rest of the sky? So TESS is actually going to address that. You'll see in this video.
During its 2-year survey, TESS will watch a wide variety of stars, looking for signs of planets ranging from Earth-size to larger than Jupiter. Each of TESS's cameras has a 16.8 megapixel sensor covering a square 24 degrees wide, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a long strip of the sky called an observation sector. TESS will watch each observation sector for about 27 days before rotating to the next. It will cover the southern sky in its first year, and then begin scanning the north. TESS will study 85% of the sky, an area 350 times greater than what NASA's Kepler mission first observed, making TESS the first exoplanet mission to survey nearly the entire sky. Because TESS's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope, which allows the 2 missions to work together to first find and then carefully study exoplanets, expanding our understanding of worlds beyond our own.
Yeah.
10.
Isn't that exciting? Yeah. So just to quickly recap the video. So on Monday, we're getting this space telescope launch, and unlike Kepler, it's going to look all over the entire sky to find planets over 2 years. And since you're not spending as much time in each sector of the sky, only 24 days instead, right? You're only finding planets that are closer into the star. You won't be able to find something like the Earth. Kepler's main mission was to find like an Earth-like planet. TESS is going to be finding small planets and big planets, but they'll be very, very close to the star. At the same time, another space telescope mentioned in the video, the James Webb Space Telescope, the current launch date is now in 2019. It's a much bigger telescope. It's not going to be doing a survey because it's so much bigger. It's a lot harder to run. You want to be using it to look at single planets very carefully and characterize them, learn about what's in the atmosphere. So in a way, TESS is kind of like a finder scope for the James Webb Space Telescope. TESS is going to find the most interesting planets, and then James Webb is going to go and look at them and really learn more about them, right? Beyond just the detection. Were there any questions? Yeah, these are just 2 of the most upcoming NASA missions that are very exciting. So the second half of this will be a tour of exoplanets. Basically a brief overview of all the types of exoplanets we have discovered during the last 2 decades. And NASA has something they call the Exoplanet Travel Bureau, which produces these very nice posters, kind of very much like the U.S. National Park style poster about all these exoplanets. So I thought they were really fun to look at, and also they're actually quite informative. So we're going to just step through them a little bit and just talk about these different types. Okay. So the first one doesn't actually have a poster. They're hot Jupiters. We kind of mentioned them a little bit already before. So, but I didn't put up against that, remember. But were there any questions about these hot Jupiters? Remember, these are giant planets that are orbiting very close to the star, maybe only 1 day to complete entire orbit. Yeah.
Could you get a result like that if you had a larger than Jupiter mass slamming into that star and then it just ejected more than a massive amount of the material to make that? Would that work?
Okay, so you're saying that the hot Jupiter could be made out of the gas from the star, something causing the star to erupt some
Erratic orbit from something pushing it in, and in an early formation and slamming into the star.
Okay.
And then you got the ejected partial Jupiter size, like the half Jupiter mass would be all that was left ejected.
Okay, I see.
Would that happen? Could that happen?
That would be a little tricky because if it's something, so like with Keplerian motion, right, unless there's something that's taking the energy out of the system, if you're coming from really far away and slamming into the star, once you leave the star, you're gonna go back to where you came from. Like that's one of the laws, like the laws of orbits. Like you always go back to where you come from, unless there's something in the system that drains out energy. But because on that idea, there is an idea where in order to get a hot Jupiter from a normal Jupiter migrating inwards, if you have another star in the system, there's some gravity interaction between the other star and the giant planet can cause it to become very elliptical, so almost like a comet-like orbit, right? Moving in close to the star, and then when it's close to the star, it doesn't actually hit the star, but getting close to the star, gravity from the star raises tides on the gas giant. This is just gas; it's very malleable material. It kind of deforms a planet, and when you deform a planet that way, you release a lot of heat, which means you are draining energy from the system. Then you can put it onto a smaller orbit. But that's getting a little bit more technical, maybe. But yeah. Yes.
These hot Jupiters that are so astonishingly close to their stars, are any of them rock?
No. So these are gas.
All gas.
Yes. Yeah. They're all. In addition to hot Jupiter, they're all. Some planets are mostly rock, very, very close to the stars as well. These are super hot cores of planets. And there's one theory that maybe those rocks that we see are Jupiters, hot Jupiters that have their atmosphere stripped away, so the only thing left is the rocky core. That's one possible explanation of how we get those.
Of our own inner planets.
No, not for our own system. Yeah, Mercury is a little bit further away, but in other planetary systems, yes. Yes.
How does it keep out from the star and not just fall into it?
Right. So in general, if things have energy, then they can remain in orbit, right? So when things are orbiting the star, they're kind of always falling into the star. But you fall fast enough, you miss the star, and then you go around, you keep falling in towards the star again. But that is a good question, because a lot of models people form of getting things to start far away and moving in towards the star, a lot of them fail because you can't stop. You just the model doesn't have a way to stop. So that means if you have something moving in, it's going to keep moving in towards the star. So yeah, I mean, so in one way, the question you ask is something scientists are still asking, like why? How do they exist? Why didn't they fall into the star if they migrated? Okay, so the next type is something you've seen before too, called super Earth. And in this poster, we have a planet system called HD 40307G. And this is a super Earth because, like I said before, it's something that's bigger than the Earth and smaller than Neptune. And in this system, gravity is about 50% stronger on this super Earth than a regular Earth, right? So if your weight was like 100 pounds on Earth, it'll be 150 pounds on the super Earth. But that also means things like your terminal velocity, like how fast you can fall, is a lot faster. So you want to do things like skydiving. The super Earth is where you want to go. Right? So skydiving can be a lot more fun or a lot more scary, especially when it's not planned skydiving. So another type of planet that Kepler has found, so this one is called Kepler 16b, or circumbinary planet. And of course, George Lucas introduced us to our first circumbinary planet with Tatooine. Luke Skywalker has the planet on the 2 stars, but it's actually about 2 dozen or so circumbinary planets already known. These circumbinary planets are generally gas giant planets. So you kind of have Luke Skywalker on these gas giant planets because it has no surface. But these gas giant planets may have moons, and these moons may be in the habitable zone. So it might be possible to imagine life, something like this, on a rocky moon of a gas giant planet in a two-star system. So I kind of mentioned something, the habitable zone. So this is a concept that's kind of also known as a Goldilocks zone. Right? So the closer you are to the star, the hotter this planet the star is. The more further you are away, the colder the planet is. So that means there has to be some place where it's just right, and in this case, just right, we say it's where liquid water can exist on the planet. And we're interested in liquid water, of course, because we're interested in life that's kind of like what we know here. But of course, we know also that alien life form could be very different from what we expect on Earth. But life on Earth kind of really needs water. So one starting point for looking for life that we can think about is planets in the habitable zone. So in this poster, it's a poster of the system, the TRAPPIST-1 system. And this is the system discovered about a year and a bit ago, and there's actually 7 planets with 3 of them in the habitable zone. And here is just imagined picture where some people on one of these, on TRAPPIST-1e, and looking out at the sky, you see 6 other planets, because there's so many other planets in the same system. For another view of the TRAPPIST system, this is kind of what the planetary system looked like. Originally, only 3 planets were discovered, and then 4 more were found in the same system. And I think this star might be observable from the northern hemisphere, because the OIA is about 23 hours, but the declination is only -5. However, it's very faint. It's a 19th magnitude star, so it might not be, definitely not naked eye observing. Yes.
I just have a question about the TRAPPIST-1 system.
Yeah.
I thought the radiation from the core star was too hostile.
Yeah, so you're right. So one of the things we talk about in the habitable zone, the habitable zone only measures temperature, right? So in this case, the middle planets, these planets here, do have temperatures where liquid water could exist, but could life really exist? And you pointed out correctly that this is a really small dwarf star. Actually, it's only 10% of the size of the sun. It's an M star, and M stars are very active. There's tons of radiation coming out from the star. So unless life on this planet is somehow hardened against this radiation, it's unlikely that we can live on this planet. But
is there some dwarf stars that are stable?
So it's not whether. So stars over time will become less active and less emitting less radiation. Just that dwarf stars have such a long lifetime, way longer than the age of the current universe, actually. So the period of time in which they're really radioactive, I guess, not quite radioactive in the sense of uranium, but in the period of time where they're emitting radiation that are dangerous to humans is a very long period of time. So it's tricky to have life there. But then there's other studies about other ways you might mitigate these effects, or different types of life forms that aren't affected by this radiation. There's a lot of stuff we don't know yet. But yeah, but that's a good point. Okay, and on this system, Kepler 186f is just pointing out that life on different planets could be very different, even if they're habitable and safe. Right? So here's the planet where maybe the grass is always redder on the other side. Maybe the stars are a little bit different, or the biology on this planet, just instead of having green plants, we have red plants. And yeah, I was originally going to use this to make a point that having liquid water is not enough to really have life as we know it. But you already made a bit better point that even having liquid water and having the right temperature doesn't mean you have the right radiation environment to live on. And then one last type of planet is something called rogue planet. So these are planets that actually don't have any stars at all. They're kind of just free-floating planets lost in space in between stars. Maybe, we don't really know how they formed. Maybe they were originally formed around a normal star system and then ejected. Or maybe there's some way for planets to spontaneously form from the material out between the stars. So the nightlife one, this supposed to suggest that the nightlife on such a planet could be very exciting because it's always nighttime because there's no star at all.
Have any rogue planets been detected?
Yes, yeah. The primary way of detecting rogue planets is different from the other two, because the two ways I showed you today all require a star because you detect them as something happening to the star. The method is called gravitational lensing, and the unfortunate thing about gravitational lensing is the method is that you can requires a lot of things happening at the right time, and in a sense, you can only see the planet once. You just detect it, and then that's it. You just know it's there. You can never see it. We can never really plan on observing it again. So that's a little too bad, but yeah. So a lot of people ask, can you get to an exoplanet? So one of the fastest vehicles that humankind have created is a New Horizons spacecraft. And the fastest one is currently Voyager 1, and New Horizons will never catch up to Voyager. But New Horizons, I picked this one because it's recently in the news. It's the one that recently went by Pluto 2 summers ago, two and a half years ago. And then this New Year's Day is going to fly by one of the Kuiper Belt objects. So this mission, this is a program. If it was going in the right direction, it would take about 80,000 years at 60,000 kilometers an hour to get to the nearest star system with a planet. That nearest star system is called Proxima Centauri, and the planet around it is Proxima Centauri B. And this was discovered maybe also about 2.5 years ago. 2 years ago, 2016. And it's also around a pretty small star. The host star is a red dwarf, about 3,000 Kelvin, or about 3,000 degrees basically, 4.2 light years away. So if you could travel at the speed of light, it would still take you 4 years to get there. If you're traveling at New Horizon, it will take you 80,000 years to get there. It's about 1/8 the size of the sun. And the interesting thing is that this planet is a rocky planet. It's a super Earth. It's a little bit bigger than the size of the Earth, about 1.2 times to 3 times the size of the Earth. We don't know exactly the mass of it yet. So in a very close orbit, 12-day orbit, it receives 65% of the Earth's sunlight. Right? It's a lot closer than the Earth, but the star is also a lot dimmer, so the amount of light it receives is not too different from what the Earth receives. So it's within that star's habitable zone as well. But again, this is a very active small star. Radiation could make life tough on it. But it's cool that this is the closest star in our system actually had a planet. And all this time we were looking for planets around stars much further away. And there's some people, like the Breakthrough Starshot mission. So I think this is founded by some venture capitalists in San Francisco. I think it's the same guy that backed Facebook originally, but now he's backing a lot of science projects, to basically send a camera at almost the speed of light to the system, take pictures of it, and somehow send the images back to Earth. It is a very ambitious project, and but it is interesting that the people are thinking about how to get to this closest system, and it probably won't happen in any of our lifetimes or even our children's lifetime. But it could happen one day. This is if humans were ever to get to another star system, this is the most likely one that we go to. Okay, that's the end of the tour of exoplanets. Is there any questions at this point?
Is there only the one planet that they found around Proxima Centauri?
That's right. There's only one planet in the system that we know of so far.
But there could be more.
It could be more. Yeah. Yes.
No, there's a close double just to the right of it.
That's right.
Alpha and
Yes, that's right.
Centauri.
Yes, I almost neglected to say that. Yes, so this is Alpha Centauri A and Alpha Centauri B, and then this is Proxima Centauri. So there's a triple star system. It's really far away. I forgot exactly how far, but they're very distant from each other. And originally, they actually, a couple of years ago, people thought that there was a planet around Alpha Centauri B, but it turned out to be not a planet. It turned out to be some weird thing the star was doing that made it look like it had a planet, but it didn't. But Proxima Centauri has a planet, so in the same system still. Okay, so the last part of the talk is going to be mostly pictures about some of the observing I have done as a graduate student that I'm very fortunate to do, and I'd like to share with you. So this part will be mostly like a vacation slideshow thing, but if I run out of time, please just cut me off. Okay, so a lot of my science is actually during my graduate time career is work is with the Keck Observatory on Mauna Kea. So Mauna Kea is mounted on the big island of Hawaii, and there's a lot of telescopes on the mountain. I'll show you some more, but the Keck Observatory is these two big domes here, and they're 10-meter type telescopes, and that's what a lot of my thesis work has been working on. And the survey that I did as a graduate student is called the Friends of Hot Jupiter survey. which is basically how did hot Jupiters get so hot? How did they get so close to the star? We thought that maybe, like I mentioned before, there's another star in the system, a friend, that helped it migrate along. So we took images. So these are some of the data that we took. Well, this is the host star with the hot Jupiter. You can't see the hot Jupiter, but then this other blob of light is the companion star. In this case, this star is about a third of an arcsecond away. So we had to use adaptive optics, a technology that allows us to really resolve a small spatial resolution in our optics system. And for this system, it's about 40 AU away. So this is this object, a system where there's a star, and then there's a sun-like star, and then there's another M-dwarf star about this, where Pluto would be in our own solar system. So it's a very different system. So that was my thesis work. And what I'm doing now is trying to directly image giant planets, look for new giant planets. And this is a system it's called HR 8799, and it's actually the only multi-planet directly imaged system where you can actually see the planets themselves. And this is the animation made by Jason Wang, a graduate student at Berkeley, and Christian Marois, who's another astronomer at NRC Pittsburgh here in Victoria. And Christian is actually the one that discovered this planetary system in the first place. And this combines 7 years of data where you can actually see the 4 planets orbiting. So this is really cool. Right? This is a system where we actually can see Kepler's law in motion. And I feel like this is the equivalent of Galileo seeing the moons around Jupiter, but this is now planets around another star system. So my goal is to run surveys to look for other systems like this one. Yeah. So now a little bit more about observing in Mauna Kea. So at Caltech, actually, a lot of our telescope access is all remote. We mostly work through a room with no windows in the astronomy building, connecting it remotely. But a couple of times I do get to go to Hawaii to do some observing. So this is the picture of the Kona airport where we land. It's just struck me that it's very different. There's basically there's security, but it's basically like just a gate. And everything is open. There's no terminal building. You just around palm trees waiting for your flight. And one thing that surprised me, because I didn't think about it very much, was that when you land in Hawaii on the Kona side, it's all very volcanic. This is the volcanic side of the island. So you don't see like the lush tropical paradise that you might associate with Hawaii. You actually see all these volcanic rocks there and interesting animals. And not on an observing trip, but on a vacation, we went to Volcano National Park. And this is a picture of one of the caldera of that volcano in Volcano National Park. And I don't have a picture of it at night because I don't have a good camera that can do like really good like astrophotography. But we came back, we saw this caldera the other day, we did some hikes. And then my wife and I came back at night, and you can see I don't have a picture of it, but you can imagine caldera glowing with lava, and then you can actually see a lot of stars in the sky. And I felt like this picture, that image in my head is a great way to encapsulate how I think about science, because I'm a planetary scientist, right? So I study geosciences of the Earth and other planets, but I also study the stars as well. And I think that was a nice merger of the Earth science world and the astronomical world. So I'll tell you a little bit about the geology of Hawaii as well. Hawaii is actually part of a long chain of islands. Like there's the 4 main islands you might know, like the Big Island, Maui, Oahu, Lanai, Sapphire Islands, and Hawaii. And then there's like all these other islands all the way out to Midway. And if you zoom out, it's actually part of a really long chain of islands, all the way up to Siberia. There's all these islands. And this is actually one of the evidence of plate tectonics on Earth. Right? There's actually a hot spot somewhere in the Earth's mantle that spews out material, molten lava, rocks into the crust. And then as the crust moves, you first form an island. These are the oldest islands. You form an island here, and the plates are moving, and then over time you start forming these chains of islands. And so that means that the youngest stuff is the stuff that's most south. Like, so on the Big Island, there's still like lava flowing. You can still see the ocean, the steam coming up from as lava goes into the ocean on some days. So that's basically the youngest of Hawaii. And then as you go up the chain, you're looking at things that are over 10 million years old, 27 million years old. So Hawaii is also a very interesting place for my department because a lot of us are astronomers. We use telescopes there. A lot of us are geoscientists. We study the really cool geology there. And this is just a quick map of what it looks like. For our observing run, we flew into Kona. So I did this with Mike Brown. Really, we could have flown into Hilo, but he likes Kona better, and Kona is pretty nice. So we flew into Kona and we drove up the road. Back then, there was the new saddle road wasn't built yet. It was in this map, so it was a little harder to get up to Mauna Kea. But what you do is you go up. Mauna Kea is about 14,000 feet. You stop at Hele Pohaku, which is the astronomer quarters, at about 9,000 feet. So this is one of the pictures, basically the main lobby of Hele Pohaku. And it's nice to see all the flags here because astronomy is a very international endeavor, right? So lots of cooperation between many countries. Right? But on the first night, you kind of arrive early, you need to acclimatize the altitude, but you also need to switch yourself onto a night schedule. So there's some stuff you can do. For one of the observing run, I watched the series finale of Breaking Bad in that TV room there. There's a library with different books you can read. I knew that some of my friends were observing a couple of months later, so I wrote a note letter to them and I hid it in one of the books, and I gave them some hints about what book it was, so they had to dig through it. And then a few months after that, I came back and they left a note for me. So we really need to find ways to like kill time when we adjust a schedule, right? There's a nice little kitchen in this thing. It's the best part of the kitchen where all the ice cream is. You can just have yourself an ice cream. There's also a visitor center where every night they actually have star parties for people who want to go up and look at. So you can see some of the scopes here. The observer domes, some pictures. These stairs, 9,000 feet, are quite challenging. When I first got up there, I forgot that it was at such a high altitude, and then I walked up the stairs, and I'm like, why am I so tired? So you have to pace yourself, and it's even more so at 14,000 feet. Here's a picture of one of the dorm rooms. The bed had like heated electronic, like these like little heating pads in them that I didn't know about, but it was very nice to keep it warm. That's just like a little toy that people in my graduate class just, whenever we went on a trip, we took pictures of it everywhere. So it's just a fun thing. And then the next day, you get to drive up to the summit. So with Subaru, you don't actually drive the vehicle. The person who's used to driving up that road drives it up for you. So you start, as you go up, you can start seeing the telescopes. All the street road signs there have like holes in them so that the wind doesn't blow them over. And then I think this is the James Clerk Maxwell telescope. And you can see that now we're above the cloud level. It's really cool. I took lots of pictures of that because it's amazing to see yourself on a mountain that's above the cloud level. And then there's something I didn't go through in the picture, but on one morning, after observing, I came out and I could see the shadow of Mauna Kea on to the water and onto the next island over, which is a very awesome sight. There's a picture of me with the Keck telescope in the background. This is some of the telescopes that Canadian astronomers use. This is the Canada-France-Hawaii telescope and the Gemini North telescope. There's a twin telescope in Chile for Gemini South. And then this is the telescope we actually, for this particular trip, we came to use, the Subaru telescope, this monolithic thing. It's about the same size as the Keck telescope. And then here's some pictures inside. So because we went there for a tour, we're always going at night. Lighting is not always as good. You want to keep your telescope optics dark, of course. So I don't have like really cool pictures of inside the Subaru. But here's what's like in the control room, like a big wall of monitors, and you set one of these things and type in commands to control the telescope. And now actually in Victoria, we kind of, on the hill, we kind of recreated something like this. This is for Gemini, but it's the same idea. We can recreate a monitor bank and then remotely connect with these computers into the computers controlling the Gemini telescope in this case. And we are also set up to also work with Keck as well. But the downside of remote observing, it does make it convenient when you don't have to travel, but you can't have nice views like this. So there was a moon set after one of my observing runs that I really like. And then, so Caltech also owns the Palomar Observatory, so we also got to observe there. And one of my classes, my astronomical instrumentation class, we took a field trip to Palomar. And so this is just the front of the 200-inch, the big Palomar telescope, the Hale telescope. But so what Greg didn't say is actually before I became a PhD student, I was not even an observer. I was a theoretical astronomer where I did all my computer simulations. So when I visited the Palomar telescope, my first year of graduate studies, is the first time visiting like a scientific observatory. And we started with the smallest telescope, and at every single telescope, it was the biggest telescope I've ever seen in my life until I got to the 200-inch telescope as well. But then a few years later, I did go back, not just for a field trip, but for an actual science study. And so there's a picture of the dorms there. It's called a monastery, because it used to be a monastery. And there's lots of strict rules about what you can do at the monastery. Right? So it says, take your showers after 1 p.m. so that you can sleep. Enjoy, like, let the dog slide slowly, quietly, walk slowly, talk softly, and basically things because people are sleeping during the day. And in the control room, there's some humor, I guess. In case of emergency, you can use this Galileo scope instead. But one of my favorite things about the Palomar Observatory is the guest book. You can look through it and see lots of excited comments. So these are some people very, very excited about seeing the observatory for the first time. And there's some things. So I guess in 2007 there was a big fire on the mountain, and then so this is from the fire department. Someone noted the fire department, and also the fire department signed it. There's some Canadian astronomers. There's Lynn Allen at BBC, and then people who. So this people think that entire paragraphs talking about how grateful they are to have this observatory and how much they enjoy it. There's Phil Nickerson, who is a professor at Cornell University, being excited to use this telescope. So that's the end of my presentation. I hope you enjoyed hearing about the science, hearing about exoplanets, and a little bit about the observatories themselves. Thank you.
Well, thank you very much for a very interesting talk, Henry. Has anyone any questions for Henry? Les?
How old were you and what caused you to decide to become an astronomer?
Yeah, so I actually did decide to become an astronomer until I was halfway through my university studies at UBC. So I guess part of it is that I didn't know what an astronomer really was when I was younger. So I'm the first person in my family to finish high school and go to college and all that stuff. So I actually didn't know that you could become a scientist by going to more school. But so it's during my university time that professor talked to me about, here's the path to academia, this is what you need to do. And so I'm very grateful to have mentors at UBC that put me on this path. But, yeah.
Anyone else? Well, I have one thing I was pondering is that it's one thing to find the exoplanets that are fairly close to a star. The atmosphere, determining the atmosphere is a challenge. Like even in our own solar system, Venus has an atmosphere 92 times heavier than that on Earth. Mars has an atmosphere about 1% of what we have on Earth. In a period of 3 planets, we have this huge range.
Right.
And is there any way that you can detect when things go through the eclipse or phase or anything like that about the nature of the atmosphere on these exoplanets?
Yeah, that's right. So this is actually a technique that my thesis advisor basically created when she was doing her PhD at Harvard. And so this is called transmission spectroscopy. So I guess, let me see, a diagram would be a little bit more helpful. But so during the transit, you see that the planet will cross in front of the star, but then when it crosses, so there's actually 2 ways you can do it. When it crosses in front of the star, you can imagine that there's a big puffy atmosphere around this planet. You're going to see that the outer edge of the atmosphere crosses in front of the star first. So that means at that moment, light from the star is passing through the atmosphere, and if there's any molecules in the atmosphere that you want to detect, it can absorb some light. So you take the spectra of the light that's going from the star through the atmosphere onto your telescope. You're going to see mostly like all the colors of the rainbow, right? But in a certain wavelengths, there can be things that are blocked off because the molecules like methane or oxygen or hydrogen will absorb some of the light. So that is the way you can probe the outer edges of the atmosphere of exoplanets. In a very short period of time, just as the atmosphere crosses in front of the star, but before the planets actually block out the light themselves. And then similarly, when you go behind the star, there's some period of time where you compare the light you see before and after. There's a period of time where the light from the atmosphere will, you don't need a picture anymore. The light from the atmosphere will be blocked from the star, blocked behind the star, so that you can see something missing. And by looking at something that's missing, you can also infer what was in the atmosphere.
So what size telescope would you have to use to detect all of these
Yeah,
findings?
so you actually need space telescopes to be doing this because you're looking at atmospheres of planets which have similar composition to atmosphere of our own planet. So say that we're looking for something like methane, the methane in our own atmosphere could block out the methane from another planet. So we use the Hubble Space Telescope, we use the Spitzer Space Telescope, and when it launches, the James Webb Space Telescope will be great.
So you must be looking forward to this new telescope going up then.
Yes, definitely. Yes.
Great.
What was that cartoon that flashed by?
Oh yeah, I think it's a cartoon of a dinosaur that says something like "Save yourself, mammals, we'll fend off the asteroids." And it's just from a science web cartoon that I really like.
Okay, well, thanks once again. As a token of appreciation, we do have our very own Royal Astronomical Society of Canada T-shirt for you, and
Thank you so much.
you're welcome.